Alright, now we're going to look at infinitely many examples by looking at conjugacy classes in Sn. So I mentioned last time this claim, although I did it at the level of cycles, so let's state it at the level of cycles, that given any k-cycle, if you conjugate by permutation, you're going to get another k-cycle of that form. And so let's do the proof of that fact. We'll call this k-cycle tau, and we'll call this k-cycle tau prime, or pi, just for simplicity. And so what do we want to do? Well, let's see what happens. So let's compute pi of something, pi of I. Well, let's look at sigma, okay. We see that we're in different cases. If I is equal to sigma of a j for some j, then what happens? Pi of I is equal to sigma of a sub j plus 1. That's exactly what this cycle thing is doing. Here it's understood that k plus 1 is 1 again. Otherwise, it's a fixed point. Pi of I is just I. So that's what that calculation on the right is doing. What is sigma, or what's tau of I? Well, what happens when I is equal to sigma of aj? Then sigma inverse of sigma of aj is just aj. Or not tau, I should be computing tau of sigma inverse, sorry about that. I'm trying to compute this conjugation. Then what happens when I hit it with tau? Tau sigma inverse of sigma aj is a sub j plus 1, because the cycle sends a sub j to a sub j plus 1. But then what happens when I compose with sigma? I get sigma of h sub j plus 1. Oh look, that's exactly what I get when I compute with pi. So when I is sigma of a sub j for some j, then I get equality between these two functions. What if that doesn't happen? Then, well, looking at sigma inverse of I, what happens when I compute tau of it? Well, sigma inverse of I is not any of these elements appearing on the cycle, and so tau of sigma inverse of I is just sigma inverse of I. Because tau only changes anything of the form a sub I for some I, and this is not one of those elements. So then when I compose with sigma, I get sigma composed with sigma inverse, I get I back again. So again, we have agreement between the two functions. Therefore, sigma tau sigma inverse is equal to pi. So conjugation of a cycle by a permutation behaves by changing the numbers inside the cycle. So then, of course, that makes you wonder what happens when you conjugate a product of disjoint cycles. Well, you can always secretly multiply in the middle between each cycle by sigma inverse times sigma. And what do you end up having? You now have a product of conjugates. Here, let me use the conjugate notation so this is a little easier. So in particular, if tau is a product of disjoint cycles, then sigma of tau, by conjugation, is the product of conjugates. In particular, we already saw that the conjugate of a K cycle is a K cycle, or of an M cycle is an M cycle. So in particular, what you see is that the set of cycles, or the cycle lengths that appear, are the same. So this is an important definition for a permutation. It's called its cycle type. It's an ordered pair C1 up to Cn, where Ci is the number of I cycles, or cycles of length I. And what we just showed is that if you conjugate by any permutation, you don't change the cycle type. Why? Because it turns out the conjugate of the product is the product of the conjugates. In this case, when you're working with disjoint cycles, and the conjugate of each cycle is another cycle of the same length. So you don't change the lengths of any of these cycles, and so you have the same number of cycles of each length. By example, let's suppose tau was 1, 3, 2, 4, 5, 7, 9, 8, 6. And suppose sigma was 1, 3, 2, 4, 5, 6, 8, and then let's include the 1 cycles here. So note, of course, you do allow 1 cycles. When you're counting cycle type, you do have to keep track of the fact that 1 cycles exist. So I will actually show the 1 cycles for this calculation. This one has cycle type 2 1 cycles, 2 2 cycles, 1 3 cycle, and then all zeros from then on out. What happens when I conjugate by tau? Well, it's equivalent to conjugating each cycle separately. So 1 gets replaced with 3. 3 gets replaced with 2. And that's how that cycle changed. 2 gets replaced with 1. 4 gets replaced with 5. 5 gets replaced with 2. And that's how that cycle got changed. 6 got replaced with 7. 8 got replaced with 6. 7 gets replaced with 9, and 9 gets replaced with 8. And so this is the result of the conjugation. And so you see it has the same number of cycles of each size. And so it has the same cycle type. And the number of such things is called an integer partition. So There's two ways to denote cycle types. I was choosing this approach where you denote it by the number of I cycles. The other way is to actually denote by the sizes of the cycles themselves as just an unordered set. And what property does that feature have? Well, then it's a bunch of numbers that are non-negative and that sum up to n. And in mathematics, that's called an integer partition. So one of the claims is that the number of conjugacy classes in Sn is equal to the number of integer partitions. Note that we haven't proven that yet. All we've managed to show so far is that if two permutations are conjugate, then they have the same cycle type. So what does that manage to tell us? So if sigma and tau are conjugate, they have the same cycle type. So the proof of the claim is actually showing the converse. If they have the same cycle type, then they're actually conjugate. Then that tells you that they're equivalent if and only if they have the same cycle type, which means that they're given by the same sum of integers, and then that means that for every integer partition, there exists exactly one conjugacy class. Of course, there's still one last step. Given any integer partition, you actually have to find a permutation with that cycle type, but that's actually not that challenging. So, suppose you have an integer partition. What that means is you have a sequence of numbers that sum up to n. And they're all integers. Well, then the easiest thing to do to prove that there exists at least one conjugacy class is to look at the permutation 1 to lambda 1 as one cycle of length lambda 1. And then lambda 1 plus 1, comma lambda 1 plus 2, comma dot dot dot, all the way up to lambda 1 plus lambda 2. This is another cycle. It has length lambda 2. And then I'm sure you can see the idea. The ith cycle as summation starts with the element I goes from 1 to, or j goes from 1 to I minus 1 lambda I. Plus 1 as its first element. We'll call this thing m for simplicity. M plus 2, comma, 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 all the way up to m plus lambda I. And so that is in fact a cycle of length lambda I. Note I'm calling it ith cycle, but orders technically doesn't matter. The whole point was to say here's a permutation that has the appropriate cycle type. It has a cycle of length lambda 1, it has a cycle of length lambda 2, and so on. And therefore, its conjugacy class has that cycle type, if this if and only if holds. And so that's part of the claim that we need, which is that for every integer partition, there exists a permutation with that cycle type. So the only thing left to prove is this reverse direction. If two permutations have the same cycle type, then they are in fact conjugate. And we will actually prove something simpler, which is that if a permutation with a given cycle type is going to be conjugate to this permutation. And why would you do such a thing? Well, because if two permutations have the same cycle type and they're both conjugate to this permutation, then they're in the same conjugacy class. And so by transitivity, they must be conjugate to each other. So let's do that part. Let's suppose we have a permutation of that cycle type. So let sigma have cycle type as cycles of length. Let's suppose we can order them. So that the length of the ith cycle is lambda I. Well then, let's actually look at sigma. Let's order it appropriately. So the first cycle I write down is C1. That's going to be A1 up to some A sub lambda 1 for some elements. Let's write down the second cycle, and up to some ordering. The order doesn't exactly matter. Then A sub lambda 1 plus 1. A sub lambda 1 plus lambda 2, and so on. The point is, any such permutation has cycles. Write down what the cycles look like, some representation, and we're to choose some first element. And now, of course, you see what you should probably define tau to be for the conjugation. Just define tau sub I to be AI. And then we'll call this permutation pi, and then you should see that tau conjugating on pi gives you sigma. And so it's probably easier to do an example instead. So let's take the integer partition 4, 3, 1, 1. So that's 4, 5, 6, 7, that's 9. What is pi? Pi is supposed to be the permutation 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, now let's just write down a random permutation sigma with the same cycle type. 3, 5, 7, 9. 1, 2, 4, 6, 8. I just chose it at random, but it must have the same cycle structure. Then you see that a good choice of tau would be to send 1 to 3. And then 3 has to go to 7. 7 has to go to 4. 4 has to go to 9. 9 has to go to 8. 8 has to go to 6. 6 has to go to 2. 2 has to go to 5. 5 has to go back to 1. And in this case, it's one big long 9 cycle. So in each case, if you notice, what's really going on here is that I'm essentially ignoring the parentheses. And here, up to the choice of order, I'm ignoring the parentheses as well. And so now I'm treating these as permutations in one-line notation. And then after doing that, that makes this so that I'm just saying, how can I get from 1 to 3? And then, well, then I need to go from 1 to 3. Well, then 3 has to go to 7. And so I'm just treating this as a permutation from one-line notation, and then writing down the cycle decomposition. So the easier way to think about this is I'm just ignoring the parentheses entirely, treating it as a permutation given in one-line notation, and then saying, what's the cycle type of this permutation, which is not the same permutation as sigma, and that actually gives you tau. Surprisingly enough, that's exactly all you need to do. And the miracle that that's is all you need to do comes down to the fact that conjugation on a cycle just relabels according to the bijection you're conjugating by. Now, a harder fact is to actually compute the size of a conjugacy class. So, according to the theorem, the conjugacy classes are indexed by integer partitions, or equivalently n tuples of non-negative numbers, where this product ICI adds up to n, i.e. Ci is supposed to be the number of I cycles. For each I cycle, you multiply by the length of the I cycle. You add it up, you better get n. Here, order actually matters now because, of course, the number of 1 cycles is different than the number of 2 cycles. So there's always back and forth in the community between which notation's preferable. I usually prefer this one because it's easier for formulas. But usually an integer partition is defined to be an unordered sequence or weakly decreasing sequence of non-negative integers. But equivalently, when you gather or count the number of integer partitions by size, then you can also enumerate them as an ordered sequence. Just the condition changes. But with this approach, you can actually give a formula, the number of such permutations, with type C1 through Cn is n factorial divided by the product. So I goes from 1 to n, I to the Ci power times Ci factorial. In particular, that is the size of the conjugacy, the centralizer in Sn of that standard permutation we had on the previous page. The algebraic proof of this part is actually pretty hard, which is why I'm not going to do it. I'm more familiar with the combinatorial proof, which is actually similar to what I was alluding to. The idea is, on the previous thing, was we were deleting parentheses. Instead, what you do is you take an arbitrary parenthesis permutation and you suddenly add parentheses. And that gives you a function from the symmetric group onto the symmetric group. Onto this conjugation, or this conjugacy class. But it's obviously not a bijection, and you just go through the proof and prove that the each preimage has the same size, and this is the size of a given preimage. But that's not a group theory proof. There's no group theory involved, so I'm not going to give that argument. It's entirely counting. And I've actually given it in the discrete math course. But it's an interesting argument, and it's one way to count the conjugacy classes. I think the one interesting example in this case that I want to notice and highlight for the future is looking at S6. So S6, if you look at the number of cycles of type 0 to 0, 0, 0, so no 3 cycle, no 4 cycle, no 5 cycle, no 6 cycle. Oh no, wait, hold on, let me get this correct. So 1, 2 cycle, 4, 1 cycles. The number of such permutations of this type, then you're going to get 6 factorial over, let's do it carefully. The zeros don't actually really matter, so the only 2 terms are the first one, 2. The first term is 1 to the 4th power times 4 factorial, and the other term is 2 to the 1th power times 1 factorial. And so what do you get? You get 6 factorial divided by 2 times 4 factorial. So you get 6 times 5 over 2, which is 15. On this related example, if you look at just 3 2-cycles, you get 6 factorial over just 2 cubed times 3 factorial. Well, that's 6 times 5 times 4 over 8, which is 15 again. So I like this example because in general, it's very rare for the sizes of conjugacy classes of permutations to match. It can happen, but S6 it does happen, and not only does it happen, but the order of this element and the order of this element are the same. And S6 is the only time where that happens, where you have two conjugacy classes of elements where the elements have the same order and the conjugacy classes have the same size. And that actually is important for some very strange fact about this group that's going to pop up later.